Okay, so let's proceed with the load forecasting case study. So actually it's a long case study. So let me just run all of the commands at once. So that's what all the IDEs of Python does. So all of the commands are run at once. But the good thing about Anaconda or Jupyter Notebook is that you can run each of them step by step, and the output and the variables are stored in a RAM. Uh, and you can basically visualize them or check the value or diagnose or troubleshoot for any issues. So if you want to run all of the cells, you can just click on cell and then run cells. So these are going to run one by one. So currently,
Can we have a little bit explanation on the data, like what fields do we have and what energy values are we trying to predict?
yes, yes. So run all, not just run cells, it is run all. So these are going to run all of the commands at once, like one by one. So here we have this pandas library that is imported. So import commands are used in this way, and there are aliases, and usually like any data science engineer or someone working on machine learning, they use PD as an alias for pandas, NP as an alias for NumPy. So also I'm like importing date time because I'm working with the time series problem. Here the problem is load forecasting, and basically we are using the data set of smart meters, which is basically recording electrical energy consumption at the household. Now, a stats model, these are the library package corresponding to the time series. Then sklearn, these are corresponding to the machine learning packages. And Keras is corresponding to the library package for deep learning. So DENS is for fully connected networks, and LSTM is for the RNN LSTM. Now, the data set that we have is, okay, let me just show you the data sets. So these are the data set, and each of the block correspond to the block of the houses. And when you open them, uh, you can also like perform the descriptive analysis within the commands over here, but it's still running. So I'm just opening the CSV file over here. Now we have the daily energy consumption is being recorded. We have the energy median, we have the energy mean, energy max, energy count, energy standard deviation, the sum and the minimum of a particular day uh, for an house ID. So this is corresponding to basically a house ID. And if you go for each of the block, there are different houses. Now these are the different houses which are corresponding, uh, which have this corresponding house IDs, and we have the daily energy consumption across time. So we are basically reading these files, the block files from there, and we only want the day, the house ID, and the energy sum. So we are filtering the data frame over these columns. We are re-indexing or resetting the index, and we are storing them into the intermediate outputs. So these particular HC files which are generated, these will contain only these three columns. So basically we are processing over here, and energy.csv is basically I'm opening in the append operation, and I am writing all the data which are available in these files, in the HC files, into the energy.csv. So finally, yes, Venom.
Yeah, the bit. Can you increase the font a little bit?
Okay. Is it better now?
Yeah, that's better. Thank
Okay.
you.
Yeah.
Yeah,
So
this is perfect.
energy.csv is basically the file consisting of all the required data. So I'm reading this file again. Now, if we are deleting the intermediary files and the original file, this still is the processed file. Now I'm basically grouping based on the house ID and day, and I'm basically getting the house count. So on this day, we have only 13 houses for which the data is available. On this day in 2011, we have 25 uh, data 25 houses data available, now 32, and then on the next day 41. So this indicates that either the data was not recorded at other houses, or it indicates that the installation of the smart meters happened over a period of time. So from the history of the data that is provided to us, it states that in 2011 November they have started installation of the smart meters in different houses, and that's why we see that over the period of time the houses which are recording their energy consumption is increasing because the smart meters were installed over a period of time. So if we plot a graph of date versus the number of houses, we see that there is a gradual increase in the number of houses. Now at this point, there were some faulty recordings, so the number of houses recording the data decreased over here. So the total number of houses, I think there are like 829 houses, and the energy sum, the maximum energy, daily energies are mentioned over here. And this is basically the energy data set that we have. We have day energy sum and house ID feature. Now, since we have like a different number of days for each of the houses, for load forecasting application, combining more than one model, example auto encoders to extract features, and LSTM to find anomalies. Is it possible? Is different from the LSTM input? Yes. So the combination of more than one model, a 1 ml model, has been used time and again. So for one of the examples which you have stated, the auto encoders is used for extraction of the features, and LSTM to basically classify the situation into anomalies and normal conditions. It is possible. There have been papers on this. Now, in terms of like output of autoencoders different from the input which is given to LSTM. So while we connect these two models together, we perform some kind of reshaping of the data or processing of the data so that the output of one model matches with the input of the another one. And let me show you. Actually, in this case study, I have also mentioned LSTM as one of the examples. So mm, here we perform reshaping at this point. Let me, yeah, here. So here, this is the train and train X and train Y, which is being obtained from the train data set and the test data set over here. But before this train X, train Y, and test X and test Y given as input to the LSTM, because the input to the LSTM needs to be like 3D tensors, we need to perform some kind of operation here. So that's how here we are doing a function which is dot reshape, and we are just adding this one extra dimension and just mentioning that it is unidimensional. And then once this reshaping is done, we are giving this train X and test X to our LSTM model over here. So this is actually just mentioning the input shape. However, this is the data train X and train X data which is basically given to LSTM. So that's how there are supposed to be some kind of pre-processing steps, and I actually explained about the filters and the padding and the strided convolution and the max pooling. These are the kind of operations that we perform in order to match our output dimensions to the input of some other type of model. So that's how like auto encoders and LSTM are used together. And also in some of the papers you see CNN models being used uh, in concatenation with LSTM, one after the other. CNN is used for the extraction of features, and LSTM is used for the final forecasting or final classification. Even in that case, so some kind of operations are to be performed. So currently, this is out of the scope of the discussion because it was just a 3 hours course, and there are so many concepts in machine learning and deep learning that can be covered, and I have skipped topics in each cases. Like I have skipped different types of statistical distribution, different types of linear models, there are different types of non-linear models. uh, yeah, uh, I hope like I have
Yeah,
answered
so I
the
guess it is
question.
possible, right? So we are trying to say
Yeah,
that
it's
yes, it is
possible.
possible to combine these layers.
Yes. So coming
Okay,
back
thank you.
over, yeah, coming back over to the topic. So now here we have the energy data set, and I'm basically here forecasting the average energy per household. So, and this is describe function. This is basically providing the descriptive statistics, and we also have the API which is called as Dark Sky API. This is an API that provides the weather station data available to the users for freemium service and for paid service. And we have used this API multiple times in our project. Um but here I have provided with a snapshot of the daily weather data that is available, and here in the next step, so these are like temperature, the atmospheric pressure, the wind speed. So all kinds of weather data information is available, and these can be merged with the energy consumption data points which was recorded in England. uh, so for example, the merge command is basically here. So we are merging energy data frame with weather data frame on the day. So day is basically a common column between these two data sets. So if someone has used SQL, so these are like two tables and we are merging them on a primary and the primary keys basically. So so these are another step, which is basically correlation analysis and also understanding how one feature varies the other features. So from that we found out that the temperature and the energy consumption, these are directly related because the overall trend is the same in both of them. And we have like, yeah, so these are like different parameters, and here there is humidity which follow the same trend. Then we have the cloud cover, then we have wind speed, so there is not much relation here. Then there is UV index and average energy plus household, where average energy is the red curve and the green is the UV index, and these are like inversely correlated. So if you go down, we also add the holiday data set, and we also perform the k-means algorithm with the number of clusters equal to 1 to 20. So we are basically ranging from 1 to 20 and checking the elbow curve. Now the elbow curve shown here is a little different because this is like in terms of score, and previously I have shown with the average distance. Now the elbow is formed at a point around 8, you can say. So the optimal number of clusters here is 8. So in this way, like we perform different algorithms. So here we are showing about the auto correlation and the time series analysis that we have performed. And Going forward, we also have different sklearn and machine learning techniques. Um, Here I am showing how the LSTM model is built. This is LSTM model. This is dense layer, which is basically fully connected network, but it has only one neuron. And the activation function, which is used over here by default, like if I don't mention activation equal to linear, so it by default means that it is a linear activation. Then I am using MAE, mean absolute error, as the loss function for regression. In classification, we have used binary cross entropy or categorical entropy, and here optimizer is the Adam function. And before we do like LSTM operation, we are also scaling the features here with the use of min-max scaler, which I have explained in the normalization, although I have not used batch normalization here. Now here this is like the average energy and the prediction. Average energy is given by the red, and the predicted energy uh, is given by the blue curve. Then also we have like linear regression. So I have basically used the default parameters, but you can try for different parameters and also follow the conventions that I have explained in the presentation. So this is lasso regression. Then there is decision tree regression, MLP regression. So this is basically densely connected neurons. And here I have used three hidden layers with ReLU activation and Adam solver. And here I am using the same deep neural networks, but using Keras API. So sequential model and the dense layers. And this is the model summary, basically showing the fully connected networks. And here finally, like we show that we have the mean absolute error of 0.66 watt hour or kilowatt hour. I think it is kilowatt hour mentioned. So here are a few of the graphs. So this is the case study on the load forecasting and how machine learning can be used for load forecasting applications. As